Okay, so section 6.3, what we're going to focus on is binomial probability. The first thing we're going to establish is what a binomial probability problem looks like. We're also then going to establish how to calculate a binomial probability. We'll give you the formula, we'll have you do it by hand, and then we'll also teach and focus on using the TI-84 to do these problems. Okay, genetics say that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has the probability of 0.25 of having type O blood. Suppose these parents have 5 children. Find the probability of. So, first of all, let's remember in words that what this means is no children with type O. That's basically what this probability uh, function looks like, or what this symbolism stands for. Now, just doing a quick complement, if it's 25% to have blood, if we do a 1 minus 0.25, then it's 0.75 of not having blood. Now, if each of these children are independent of each other, right? Independence being key. We know from chapter 4 that we can multiply, so we can go 0.75 times 0.75 times 0.75 times 0.75 times 0.75. And if I type that in on the calculator, 0.75, what we end up getting is a probability of 23.73% of this happening. Now, if we go the other way, if we look at this one, we say all 5 children are type O. Then it's also just another generic standard probability, except now all right, 25, 25, 25, 25, and 25, right? And if we do that, um, and calculate it out, then we're looking at a really low probability, under 1%, 0.09765 6%. So really low probability of that happening. Um, let's also just keep in mind for future reference that instead of typing in all this multiplication 5 times, I could have just went this to the 5th, or I could have just went this to the 5th. Now, let's get at the crux of the issue. And the crux of the issue for binomial distributions really start here, because the problem with having exactly one exactly one child with type O blood is that there's a bunch of different ways we can do that. We could do 0.25, so that's one, right? And then the rest of them do not have type O blood. Or, big emphasis on that word or, we could have first child no, second child yes, third child no, fourth child no, fifth child no. Or, big emphasis on or, think mutually exclusive and addition rules. We could have no, no, yes for the third child, no, no. Or, and again, notice how long this is getting, 0.75, 0.75, 0.75. We get to the fourth child that has it. And then finally, exhaustingly, or 0.75, 0.75, 0.75, run out of room on my screen, 0.75, and then finally the fifth student has a 25%. Now, these are all mutually exclusive cases. So if we find the probability of this, we can add it with the probability of this, add it with the probability of this, add it with the probability of this, add it with the probability of this. Um, I'll come back to making this into a binomial setting, but this is the crux, especially once we get to x equals 2 or x equals 3, then it can really get even messier. So let's establish what a binomial situation is in this context and why this is one. Okay, we use in stats a mnemonic BINS, 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 to establish that this is a binomial setting. Binary meaning like binary code 0101, that there are only two possible outcomes. And generally, we define this as success or failure, though the word success or failure do not have to be in the problem. This one above with the type O blood, we would define success as having type O blood and failure as not having type O blood. So we can't have a third option. There can only be two possible outcomes, this or that. All right. The second thing is they have to be independent. The trials must be independent of each other so that the multiplication doesn't change the probability of success. So this is independent. It specifically says independent, or we'd have to find a way to assume that it is independent. The N stands for number of trials, meaning the number of trials must be set in advance. We must know. In this case, we have 5 children. That's our number. Our N equals 5, right? When our N equals 5, we're not framing the question as let's keep having a child and then stop after we have one with type O blood. We're saying no, we're having 5 children. What's the probability or the number of type O blood children we can expect? And then finally, the same probability, this kind of ties in with independence. P, the probability of success, must be the same for each trial. In this case, it's 25%. It can't be 25% for one child and then 30% for the next child and then 15% for the third child. They must all have the same probability of success. Powering on. Keep erasing. Okay, so here's the binomial probability function, right? And we'll go through what each of these pieces down here mean, but this down here is the binomial probability function. And really, I want to focus on this case that we had already wrote out. Essentially, we had wrote out a bunch of versions of this. And if we simplify some of that using math, remember exponents being repeated multiplication, it was this. We had one child with a 25% type O blood and 4 children with not having type O at 75%. Now, if you remember back that we had 6 different possibilities to add together there, I think 6. The question is when all these match, and they will, when all this here matches, how many times do we got to add them together or use multiplication to get to the total? Well, what that really comes down to is a simple combination problem where we have 5 children, choose one. 5 children, choose one. So if we do 5 children, choose one by this, see if I can find it on my calculator here. So that there wasn't 6 outcomes, there were 5 outcomes. My fault. So basically, with all that we would have added together before, if we would just type in this line right here, it would give us that answer. So 5.25 to the power of 1, 0.75 to the power of 4, we get a probability of 39.55%. So what? So this is a fancy formula. This is the probability of success. This is the probability of failure. P plus Q will always equal 100% or 1.00 because it's a binary situation. There's either this or that happening. There is no third. So 100% of the time, one of these two things happen. This, which would also be this, is the number of successes. And this total thing is saying, hey, where N is your total number of trials, this is saying total number of trials minus successes, which basically just means number of failures. So for that fancy textbook looking formula, I essentially write this out in my own personal notes for stats as this. Okay. Number trials, choose number of success times probability success to the power of number of success times probability of failure to the power of number of failures. So that's where we're at with that. Here's what I'm going to do. Moving on to the next slide then. Let's look at some of this. So if we want to start using our formulas here, we'd say N 12 choose 2. Probability of success is 0.2. And we want 2 successes. Now we go 1 minus 0.2. We know the probability of failure must be 0.80. And then out of 12 minus 2, that must mean there's 10 left. Notice that the 2 plus the 10 equals our 12 total trials. Right? And if we type that out, 12 choose 2. And then 0.20 to the power of 2, 0.80 to the power of 10. We get something like 0.2835% just for that, without any context. All right, so we go to set this one up. We go 15, choose 11. 0.9 is our probability of success. We want 11 successes. Must mean 0.10 to the power of 3. I'll leave it to you to punch that in your calculator and see what it comes out to. And one final one then, 7, choose 4. Probability of success is 1/3. We want 4 successes, which means the probability of failure to get it to add up to 1 is 2/3 to the power of 3. Again, I'll let you use a calculator so I can keep this somewhat brief to see that what those values are. Now let's get into some more fancy words here, and we'll talk about some of this. So notice this is one failure, right? So for number 4 down here, we're talking one failure. We can do this one of two ways. Probability, this right here stands for probability of success. So if we want one failure, that can mean so if we do this all in frame, if we turn the failure into a quote unquote success, we'll say 15, choose 1. We'll say that probability of that failure is 0.01 and we want 1. So then the opposite is that. That should come out to the exact same if we do this. 15, choose 14. Instead of framing it as failures, we'll say set successes and 0.99 to the 14th or zero point zero 0.01 to the 1. Um, Essentially, this combination is equal to this combination, and then we're just multiplying in a different direction. But depending on how you want to get at it, either one of those should work out. Now, at least 3 successes when we have n equals 6 trials. Here's the problem. This is probability of at least 3. So 3 works, 4 works, 5 works, and 6 works. So now we're getting right back into, that's all at least, right? 3, 4, 5, 6. If we're going 0, 1, 2, 3, 4, 5, 6. These are all my at least sixes. So now I'd have to do this formula for 3. 6, choose 3, 0.35 to the 3, 0.65 to the 3 plus, and then start over. 6, choose 4, 0.35 to the 4, 0.65 to the 2, so on and so forth. So you can see where that starts to be a real pain in the butt. And so this is screaming for a calculator, which we'll get to here in just a little bit. But I want you to appreciate the need for a calculator in this word at least. This at least is something you're really going to have to focus on. So no more than 3. If we're talking here in number 6, moving on to number 6, that's we get x equals 3, x equals 2, x equals 1, and also x equals 0. You can have no successes. So again, we have the same problem we had over here in number 5 in terms of the need for the calculator, but we need to understand why in a 100 trials, no more than 3 successes implies that this, and this all need to make it into our calculation. So let's get on to looking at how to use a calculator and then talking about issues with the calculator. First of all, you want to find it on your calculator. You're going to go to the second vars. What we're going to do is the calculator has a PDF function. The PDF function does for x equals an individual number. X equals an individual number. So you want to find a second vars and distribution menu, and then you'll find the binomial PDF function. PDF, not CDF, PDF. All right. And then we'll be able to use that function. So what I want to do is go back then a couple screens and show how we could calculate and get the exact same thing. So on our calculator here, we go binomial. So second vars, distribution, keep scrolling down. Eventually you're going to find PDF, and it may be off the screen. You just got to keep scrolling down. If you're on one of my newer calculators, it's going to pop up and say, hey, trials, p-value, x-value, and then it's going to tell you to paste. So when we put 12 in, the p-value being 0.2 and the x-value being the number of successes, 12.2 and 2, and then we hit paste, it's going to pop up like this. And what our expectation is in this class is much like when we were doing normal curves. You're more than welcome to use your calculator, but you must write out the calculator function on your worksheet to show your work. If you don't include the calculator function, your answer will not be accepted. So if we look at number, and then I hit enter, and I think this is the exact same thing we got earlier when we did it by hand. But the way this one will look is this or this for this last one. you can go back and verify that these would hit all the same numbers that we had before. Okay. More importantly, I want to go one farther forward. Well, not more importantly, but now let's talk about a little bit the cumulative binomial, so CDF. Your calculator for the CDF is figured or programmed as x is less than or equal to a number. So I'll give you an example off of a slide ago, a couple minutes back, where we were talking about this very last one, number 6, right? Where we said, okay, so no more than 3 successes is 0. You would have two options here to finish this problem. You could do the PDF of the binomial PDF 100.01 0 successes plus the PDF of 100.01 1 success plus PDF 100.01 2 successes plus PDF 100.01 3 successes. You could do all that and it will give you an answer. You hit equals. That's still a lot. It ends up being a lot of button pushing. It's a little less than if we'd have done it all by hand, but it's still a lot more than I want to do. So now, know that no more than 3 successes can be written with an inequality sign like this, right? So what that implies is that we can use binomial CDF, cumulative function, that will put us in an inequality world, which will basically do all this in one fell swoop. So we go second, vars, clear down, it's about the 7th, 8th, 9th, 10th one down. CDF, number of trials, is 100. The p-value is 0.01, the value of success or probability of success, and we want to go all the way up to 3. If you type in all this stuff, this in blue, hit equal, or type this in with one function, hit equal, it's going to give you the same thing. So I want to talk to finish up this first video, this part 1. I want to show you some issues with using this CDF function, because as we get going, that's where most of your problems are going to be. Okay. So first, exactly 2 successes implies this. You need to know that means binomial PDF, not CDF, PDF. And then you can say 10.4, darn it, 0.4 and exactly 2. Or this being an inequality binomial, this goes exactly to CDF. This is what the CDF is built for, 10.4 and 2. Now, the issue is with this CDF is when these signs start to be arranged differently than the way the calculator is programmed. So if we have 10 trials, that means you could have 0 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 trials. All right. So if we want to go less than 2, when we do this, we got this is probability of x equals 2. When we did this second one down, this is x equals 0 plus x equals 1 plus x equals 2. When we get down to this third one, we don't want to include 2 anymore. So now we want to do x equals 0 plus x equals 1. We don't want to include 2 because we want to be less than 2. So now when you can either PDF plus PDF, or what I like to do is go binomial CDF 10.4, but then I only go up to 1 because I only want to include 1. I don't want to include 2, right? So now I want to skip down. I'm going to skip down to this last one first. When we say greater than two successes, if we look up here at our sample space, greater than two successes means three or higher, right? And that's a whole bunch of PDFs to type in, so I'm not doing that. What I'm really going to do is make use of a complement rule. So greater than always implies complement. What I'm going to do is 1 minus binom CDF 10.4 all the way up to 2, because when I do up to 2, that gives me that probability. I subtract it out because it's not in the sample space I want. And then the last one that can really trip people up is now all of a sudden greater than or equal to do 2 or more. So now we're saying we want all this sample space. So the only stuff we really want subtracted out is just 0 and 1. So I go 1 minus binom CDF 10.4 and up to 1. So you got to know the difference. This has confused more than enough people over the years, not only when to use PDF or CDF, but when this last number is 1 and when this last number is 2. Um, Once you can really handle all that, then the context is the only thing left to battle.